All right. So yeah, thank you for the intro. My name is Rhys Compton, and today, along with Lily Zhang, I'll be talking about some work done during my time at NYU. Papers called "When More Is Less: How Incorporating Additional Data Sets Can Hurt Performance by Introducing Spurious Correlations." This was presented at the conference Machine Learning for Healthcare this year. The paper link and the link to the code can be found on the bottom left. So I'll just set up sort of the problem and how we're looking at this first. So we're looking at the effect of additional data sets, and the data sets that we use are these four listed here: Mimic, Expert, Chest X-ray 8, and Pad Chest. These are all publicly available data sets, so it makes our results fairly easy to repeat. And we use the term domain, hospital, environment a little interchangeably. The model that we use when we're looking at the problem of disease classification, the DenseNet 121, previous work showed this to be a pretty strong baseline. And I've also listed the key hyperparameters here. So the key evaluation metric that we use during our work is called worst group accuracy. We define it over two hospitals, in this case A and B, and it also looks at the positive and negative class individually. The way this works is it can only be high when the model performs well on both classes, both internally and externally. This is important because it really simulates and emulates well real-world deployment and a validation setting in medicine. So it's a very sort of practical metric to use. This is commonly used elsewhere in the spurious correlations literature. So the way we calculate it is we have a base hospital and an additional hospital. We first train a model for predicting a certain disease on the base hospital, and we evaluate it on the base and the additional hospital by calculating the positive and negative accuracy on each hospital individually, and then taking the lowest of those as the final metric for this run. We use the terms positive and negative accuracy, but as an aside, these have direct analogs to sensitivity and specificity, which some of you may be more familiar with. So after we've done this training on the base hospital, we include an additional hospital in training. So we're training on both the base and additional. We perform the same evaluation across both hospitals, and then again, calculate positive and negative accuracy and take the worst. And this sort of allows us to encompass the effect of what happens overall to performance when you include this additional data set during training. And I want to emphasize the additional data set that we're using is also the one that we're including in evaluation. So it's kind of a best case scenario. So coming to some key results, as the title here says, we found that surprisingly adding additional data can hurt performance. So this graph here shows on the y-axis the relative difference in worst group performance when you add a certain data set. The x-axis, these are all grouped by the different diseases that we looked at. And we looked at all sort of possible pairs of data sets that we could with those four open source ones we had. So we wanted to really, look at the question in a very wide-ranging and holistic view. And yeah, as lines here show, a bar being above y equals 0 is good. It means that adding the additional data set improves worst group performance, and vice versa for bars below y equals 0. As you can see, we have the somewhat surprising result that often, in our case, around 43% of these different data set and label experiments, including this additional data set, actually decreases performance. And again, this additional data set is from the same site that we used in evaluation. So it's really a best case scenario for adding data because we're evaluating on that same test domain as well. So the next question obviously is, why does this occur? This is a somewhat surprising result. It occurs because of the learning of spurious correlations, which is a relationship between two variables in your data that mightn't be a connection that you want to sort of use during training. Might not sort of be a desired connection. In our case, this is a correlation between the hospital of origin for an image and whether that image, whether that instance is diseased. So our 4 data sets that we use had very different disease proportions shown in the table below here. So when you combine 2 data sets, this creates a spurious correlation between the hospital and the label. This is concerning if the model can predict this extra variable, hospital in our case, because it may learn to leverage that instead of the label. So just to be more specific here, if you imagine combining CheckSpurt and the NIH dataset for predicting edema, over 92% of diseased examples come from CheckSpurt. So a model may rely on, rather than predicting the actual physiological signals, just predict which hospital an image came from, and that will have it perform pretty well overall. So this issue of spurious correlations is it really becomes an issue when the model can predict what this extra variable is. So if the model can predict hospital. And what we found is that this is the case very strongly with chest X-rays. The hospital signal is very strongly embedded in chest X-ray data. So the first way we did that was just training a CNN model directly to predict hospital, and we found that it can do it perfectly. But as you can imagine, in a chest X-ray, there's lots of little artifacts outside the region of interest, left-right markers, other sort of metadata in chest X-rays. The model could be looking at that also. What we did is try progressively smaller and smaller center crops on the chest X-ray, and we found that a model can still predict hospital very, very accurately, all the way down to an 8x8 center crop, which is a pretty important result, showing that this hospital signal is very strongly sort of embedded in chest X-rays. It's not just the outside parts of the image. It makes it very hard to get rid of. Other work has sort of shown similar results. You can train a model to predict hospital, age, etc. But we took it a step further by looking at the disease prediction models that we trained earlier. So these were the models that were trained to predict pneumonia, edema, etc. And we queried the embeddings of these models and tried to predict which hospital an instance came from using these embeddings. These were the embeddings that were trained to predict disease. And as we found, these model embeddings are also very predictive of hospital, even between hospitals that are not seen during training. So not only can you obviously train a model to predict hospital, if you're trying to learn disease, the model in this case is still learning hospital-related signals. So we learn the strong hospital signal even when we're not trying to. A quick aside, we found also that the effect of this additional data is very disease dependent. So this is just a crop of the same plot showed earlier with pneumonia and cardiomegaly. And you can see, for pneumonia, it's a lot of significant degradations, whereas for cardiomegaly, the effect of adding data is almost universally positive. We hypothesize that this is possibly due to the relative difficulty of each task. So if instead of looking at like relative change of worst group performance, which we have on the left, if we just look at sort of the median worst group accuracy, pneumonia is much lower, signifying it's maybe a more difficult task to learn. And because it's a more difficult task, it may sort of encourage the model to rely more on shortcut signals, which is why when you combine the data, that causes more significant degradations. But the point sort of to get across with all of this is that it's really important to analyze the effect of adding different data, any other ML model changes that you want to make across different labels in a very sort of fine-grained way. So we come down to the second key result, which looks at balancing as a way to help this. So balancing the label proportion between domains, or between hospitals in our case, is a commonly proposed method sort of to help fix this learning of spurious correlations. We do the balancing by undersampling the majority, typically negative class, as previous work shows this to be sort of the optimal way to sort of undersample. And so what this plot here shows on the left, it's the same plot as we saw before, comparing the relative difference of single data set performance versus two data set performance. On the right, it's a similar plot, but comparing single data set performance to two data set performance after you've applied this balancing. And you can see, overall, it's a more positive trend. More often, adding this additional data is beneficial to performance, but it's not always a guaranteed improvement. So yeah, overall, the effect of this additional data is more helpful when the label prevalence has been balanced between the two data sets. We also want to note, obviously there's a trade-off when you're doing this balancing between dropping data and fixing the spurious correlation that you might have induced when you combine the two data sets. Because undersampling removes data. So what this plot here shows is the relative difference in performance between training on two data sets and training on two data sets after balancing. So you can see, most of the time it is better to train on two data sets after balancing, but you're obviously dropping data, and so some of the time this isn't a beneficial change to be made. So, to be more prescriptive, when is balancing most beneficial? In our case, balancing is mostly beneficial when the data sets that they're using have significantly different disease prevalence. So in these plots on the x-axis, we have the log ratio between the base hospital and the additional hospital. Going further to the right on the x-axis means a greater difference in the disease prevalence between these two hospitals. And the y-axis is overall performance. And so, the y-axis is the relative difference in performance from balancing. So, a positive slope here means that as the difference in disease prevalence between the two hospitals increases, balancing becomes more beneficial. So just to wrap things up with some takeaways and conclusions, we note, first of all, there's a trade-off between adding more data to train your ML models and inducing potentially inducing a spurious correlation. It's certainly not the case that more is always better. We note that the benefits of adding this data can be very disease dependent, so it's important to evaluate your model across a wide range of diseases, different tasks that you have available to you. We find that the greater the difference in label proportion between your two data sets that you're combining, the greater chance of learning a spurious correlation and the greater chance of having the degradation that comes along with that. This is because these hospital-specific artifacts are very strongly embedded. We looked at it, just in the chest X-ray context, but there's a lot of other work that looks at other modalities, other X-ray types that shows similar results. That hospital-related signal is very strongly embedded in medical images. And finally, looking at a way to fix this with balancing, we find that the greater the difference in label proportion between your two data sets that you're combining, the greater chance of improvement that you'll get from actually applying the balancing, as this is kind of closely tied to number 3. So just to provide a little more theory, I'll pass it over to Lily to talk about when we expect balancing to work.
Thanks so much, Rhys. So I'll be talking very briefly about a separate but related work in this space. And in particular, if we assume that our data generating process comes from an anti-causal model, here we have our label Y, such as disease, and some nuisance variable Z, such as the hospital source itself, affecting or causing our input X. What we're doing here when we balance is we're specifically breaking the marginal correlation or the marginal dependence between our label and our nuisance. In other words, when we're balancing, we're learning P of Y given X under a new distribution. Rather than P train, we're looking at some new distribution, which we'll call here P independent. However, when we actually are learning our predictor, we're conditioning on our input X. So even though we've enforced a marginal independence between Y and Z, this dependence no longer necessarily holds when conditioned on X. And here we have X as a collider. And so oftentimes we do not have this independence. We find in our work that in particular, when this independence does not hold, balancing, or namely learning P of Y given X under this new distribution, can perform poorly, in fact, worse than even performing without any covariates at all, under certain test distributions where our relationship between Y and Z has changed. So based on this insight, our one simple thing you can consider doing is, instead of considering X, coming up with a representation R of X such that this conditional independence continues to hold. We call these representations uncorrelating representations, and we show that the predictor P of Y given R of X under this balanced distribution has performance guarantees when other predictors, such as the ones we had previously described, do not necessarily. We have an algorithm to particularly target this predictor, but more broadly, there are various theoretical results that dovetail quite nicely into many of these empirical results that we've just shown, or Rhys has really nicely described previously. And with that,
Cool.
go ahead.
Thanks. Oh yeah, thanks. So yeah, that's the end of the talk. Yeah, thank you all for coming. Thank you to the organizers for putting this talk on, and yeah, we'll pass it off for questions.